All right, well, hello everybody. Welcome to the Bureau of Economic Geology's summer seminar series. I'm Evan Civil, and I'll be your host today. As many of you know, this series is designed to showcase more than just the work we do here at the Bureau. It showcases the hobbies and the interest of our researchers and staff, as well as a few guests from outside the Bureau who might have topics relevant to our day-to-day lives. Our speaker today is Dr. Toti Larson, a research associate at the Bureau of Economic Geology. Toti is a geochemist and the acting PI of the Mudrock System Research Laboratory, or MSRL. His research focuses on geochemistry, chemostratigraphy, and stable isotopes applied to geologic systems. Before coming to Austin, Toti worked as a team leader for Los Alamos National Labs in the Geochemistry and Geomaterials Laboratory. As an intro to his talk, many years ago, Toti began working with the Department of Energy with colleague J.P. Decaux on a grant looking at dissolved gas and groundwater samples at fracking sites in the Barnett Shale. Through a strange turn of events, we'll soon find out, he began to apply these geochemical skills to make the perfect ice cube. So I think we're all very interested in this talk. Before we begin, I ask that you silent your microphone as a respect to the speaker. If you have any questions, please feel free to ask them in the chat, and Toti will answer them at his first availability. So I will now turn the talk over to Toti.
All right. Thank you, Evan, and thank you, Jana, for organizing this. Can everybody hear me okay?
Sounds good.
Okay, great. Well, thanks for organizing the summer session. It's fun to sort of talk about the other things we do when we're not doing the science that we spend most of our time doing. My name is Toti Larson. Yeah, I'm a geochemist, and I do study stable isotopes, dissolved gas, basically all sorts of geochemistry applied to a lot of different rock systems. And what I'll show today is kind of like Evan said, it's a weird turn of events, but like all geologists or all scientists, you make an observation and then you try to figure it out. And so what I'm going to talk about today is this, the title, the geochemist's journey to making the perfect cocktail ice cube. So you might ask, what exactly is the perfect cocktail ice cube? And I think this picture here kind of shows it nicely. It's a cube. There are other shapes that you can make ice with, but if you're going to call it an ice cube, it's got to be a cube. So the first step in the perfect cocktail ice cube is that it's right here. It's a cube. The second thing about cocktail ice cubes is that it's got to be clear. Now, clarity, it serves a lot of purposes here. One of them is function, which is if you have a clear ice cube, it's going to be very dense. It's going to be pure. It's not going to have any impurities inside of it, and we'll get into discuss later what those impurities actually are. But importantly, it's going to be very dense, and the effect that's going to have is that it's not going to melt in your cocktail. And if you're spending all your time buying expensive ingredients and mixing up, as a mixologist, mixing some nice cocktails, well, the last thing you want to have happen is dilute it with water with a bad ice cube. So you're not going to get that as quickly when you use clear ice. So that's one thing. Secondly is appearance. And let's be honest, when you're talking about cocktails, appearance is a key ingredient to have in the perfect cocktail. And these things are beautiful. These are way better than anything you're going to get out of your refrigerator. And so it's really important as a kind of purveyor of some of the finer things in life to be able to put ice cubes such as this into it. Now I'll go over the journey, and certainly I started trying to make these things, I don't remember exactly, 4 years ago maybe, but the journey really begins way back further into my childhood. I was born in Michigan, raised on a lake, and there was an observation made growing up on lakes, which is lakes freeze clear. And so I'll get into that observation and how that came into some conversations that I had with other people at, enjoying the cocktail. And when the conversation comes up about what's clear ice, what's white ice, what's cloudy ice, and you can hear all these different examples of what cloudy ice is. And I'll go over some of those hypotheses that people throw out there. And all the while I'm listening to these ideas people are throwing out, I'm thinking back to, when ice forms on a lake, it forms clear. And so why is that? And then, as you'll see in this talk, I try to apply that process to make perfect ice cubes. So before we dive into too much more, let's talk about ice. Like, why is it important? Well, ice fundamentally changed the world. going back in geology, you can go into the Pleistocene, you can go through the glacial periods. I mean, it affected how humans migrated around the world. But more recently, prior to the 1830s, food preservation globally occurred through these processes of salting and spicing, smoking, pickling, drying. The human diet was basically affected by the fact that we didn't have a lot of different preservation techniques. And in fact, there was a lot of death that would occur just from meat going bad. That was, people that couldn't store meat correctly or would try to. There was a lot of deaths that were attributed to our inability to refrigerate or keep things frozen. So who comes to the rescue here? Well, it was a person by the name of Frederick Tudor, nicknamed the Ice King. And Frederick Tudor pioneered international ice trade. He founded the Tudor Ice Company. He was one of the first millionaires to live or become a millionaire in Boston. And his source for ice were frozen ponds in New England. So where did this all begin? Well, the idea that Frederick came up with was when he was 22, and it occurred while he was enjoying cocktails with his brother in 1805. And from the accounts of the discussion, it sounds like it was almost a joke that they could somehow take the ice that was forming on their pond, harvest it, and then sell it at ports in the Caribbean. And I can absolutely imagine a conversation like that starting. But then the fact that Frederick Tudor actually jumped on it and did something about it is kind of what makes him so special, and it makes him the ice king in the ice world. So I put together, certainly not a complete, but it's a timeline just to give you an idea of the U.S. ice industry. And I think for a lot of people, it probably comes to a surprise that there is even an ice industry. But in the 1800s, this became a massive industry. And the little bit of research I did on it, I think the total number of employees was in the order of 90,000 people in the U.S. were involved in harvesting and transportation of ice. So it begins in 1805 over cocktails, like all good conversations. There's a cocktail involved with his brother. In 1806, they harvested and shipped 130 tons to Martinique, which is an island in the Caribbean. And just for reference, 130 tons is about 260,000 pounds. So that's 26,000 10-pound bags of ice. There's a lot of ice. And you think about just the logistics. This is early 1800s. How do you refrigerate it? How do you harvest it? How do you store it? How do you transport it? And once you get it there, how do you distribute it? So there's a lot of technical difficulties that go into this industry. He didn't make much money. My understanding is that it cost him about $4,600, and he made about $4,000. So it was failing at first, but then he continued. 1807, 240 tons were shipped to Havana. And there's a big time gap in what I could find between 1807 and 1833. And think of the U.S. back in that time. There was some embargo trade wars that were occurring in the early 1800s. There's the War of 1812. All of these things affected the ice industry. But think too, if you're trying to ship 100 by 1833, 180 tons to Calcutta. First off, that's a 4-month boat ride. So the infrastructure that's involved in getting to a point that you could globalize the transport of ice from New England everywhere. There's ships to be built. There's refrigeration. You can't just show up in Calcutta with 180 tons of ice and expect somebody to do something with it. You got to ahead of time build the ice houses. So it was a huge industry that was going in. And finally, by the mid 1800s, he was the Tudor Ice Company was shipping 150,000 tons of ice per year to 43 countries. And as I'll get to, and you'll see, like all good things come to an end, this form of ice industry was just destroyed by not only electricity, but refrigeration. And we'll get to that in a little bit. So how do they do it? And like I said, I grew up on a lake, so this is a very familiar scene to me growing up. And there's a couple key observations in here. I call this the lake freeze approach, and we'll get to this in a little bit. This is a picture, later, 1925. It's an ice harvest in Maine. But by the picture, it's people with rakes and pickaxes and saws and horses. My guess is the technology they're employing in 1925 wasn't all that different than what was employed in the early 1800s. One key observation to be made is that it's obvious now, but ice freezes from the top. So this is a top-down approach. Ice freezes from the top, but in lakes, there's always available water down on the bottom. And that's going to become really important to describe the process that I use. So we're going to keep moving on with this lake freeze approach. You know, clear ice, it was highly sought after for a variety of reasons. And I mentioned it in the introduction. One of the key things is that it melts very slowly. And so if you're building an ice industry and you're looking for sources, you can imagine that if you're basing it off of small lakes like this in New England, you're quickly going to run out of real estate. You know, ice starts to freeze depending on the year, you know, December, mid-December. And by the time it gets to the thickness of something like this, you know, at least a foot thick, you know, that could be mid-January. So you might only get, you know, 1, possibly 2 ice harvests in a year. And so when you're trying to globalize this, there's going to be a supply line crunch. And so you're going to go look for additional sources. Well, I can think of one place I'd go to if I was looking for some really clear, massive source of ice. I would go right to Michigan. I'd go to the Great Lakes State. Here's a picture from the NASA Earth Observatory showing the distribution of the Great Lakes. Lake Superior up here, Lake Michigan over here, and finally going down into Lake Huron. This became, you know, prior to the gold strike, prior to the oil rush, it was the ice rush. Staking claims on land that was available to get ice was a big deal. And there are ports, there are transportation, there's all sorts of networks that were built up in the Lake Huron area, up here in the thumb of Michigan. And it was a big deal. You know, you can imagine, I said the gold rush, I said the oil rush, I said the gold rush, or the ice rush. Well, you know, you can see some of these ads that people are having here. You know, we've secured an inexhaustible supply of clear, pure ice. Oh man, well, that's just like a purveyor of ice's dream come true right there. Taken from Crystal Lake. You think you'd name that to try to get people think that it makes clear ice. So there was a lot of ads. There was a lot of competition. There are a lot of people working to make, to harvest ice. And again, like that date up until about the 30s, you know, it was electricity that eventually overtook. You know, once electricity was able to make artificial ice, then this work was no longer needed. But you can just appreciate all the labor and how dangerous it was. I mean, this was incredibly dangerous. You know, growing up on a lake, being the youngest of 3, by the way, you know, I was the lightest, so I was the one that had to test the thickness of the ice. And when you find out it's not thick enough, it's a horrible situation. So it's tough work. It's dangerous, it's difficult, but the important thing here, they had clear ice. That's important. As far as numbers go, the US empire in ice, you know, we competed with Norway. It sounds to me like Norway actually was a little bit larger than the US was, but in its peak, you know, you're looking at about 90,000 employees that were harvesting ice. I tried to find stats on it in terms of the ice industry versus the other, you know, obviously larger industry in the US, the cotton industry, and I haven't gotten any numbers on that yet. But it was you know, if you're up in north, the ice industry was a big deal for a short period of time, 2 to 3 months out of the year. Well, let's move forward up into the 1950s. How do we go wrong? What happened? How do we get away from that clear ice that we all, you know, would have enjoyed back in the 1800s and early 1900s? What marked the end of the ice age? Well, here it is. Here's the patent. Edward H. Roberts, Erie, Pennsylvania, invented the freezing tray, 1952. You can see it right here. And I think for those of us of a certain age, we're familiar, we've had these, we know exactly how to use these. In fact, me growing up, you know, we would wrap these things in saran wrap, we'd fill them up with Kool-Aid, put little toothpicks in it, and we make little popsicles in it. Like all things, this is, it was an improvement for sure, but it was an improvement that did not improve the quality of it by any way. And you can see in this picture right here, the problem at hand. Clear ice forming on the outside, and then cloudy ice forming on the inside. And this poor soul, you know, trying to make a beautiful cocktail and is left with this just god-awful cloudy ice cube. You know, I can't think of anything worse. But this began in the early 50s, and it's just propagated. In fact, it just keeps getting worse. whoever this person was that invented the crescent-shaped ice cube, this is horrible. New and improved in this case definitely equals worse and more expensive. The crescent-shaped ice cube, we all have these. I have these things in my freezer. I tend not to use them if possible. I drink clear ice cubes. I drink glasses of water with clear ice cubes. These are just horrible, and it just points to the issue. What is all this cloudiness in here, and how does this actually form? Well, let's go back to think of the how this forms, and let's go back to what I said. This is actually the lake that I grew up on in Michigan. I took my kids to it, my family to it several years ago, and myself growing up, we'd always head out to the ice, and then, like I said, it always started out frozen, perfectly clear. We'd actually kind of rub it with our palms to make it kind of a magnifying glass in it, and then you can look down and see the ripples that were forming, above wave base. And you can even see some of the bioturbation that was occurring, the clams and the different organisms that were still moving around. You could still ice fish out here. So these are great days. These are magical days of ice. This is making clear ice. And so the question becomes, how can we duplicate this process and make clear ice so we can enjoy perfect cocktails? Well, before we do that, let's go to the common hypotheses. Clear ice it's a long-standing conversation. Anyone has come up with sort of different ideas of how you actually make it. And it's an interesting aspect in terms of all these bulleted points here. None of these are wrong, but they're certainly applied incorrectly. And so these are I just listed some of the common things that I'll hear people talk about what you have to do to make clear ice. Boiled water, it's a very common thing. And I'll present a slide on that shows what that does. It's not wrong, but it certainly doesn't work. Doubly boiled water. I mean, what the heck is that? And why not why stop at doubly? I mean, why not go triply, quadruply boiled water? It's just, we don't know what's going on here, why this person thought you needed doubly boiled water. This is a very common approach. Distilled water is the answer. This is suggesting that the impurities are going to be dissolved contaminants, maybe total dissolved solids, bicarbonate, alkalinity, that might affect it. But we'll get into that. You need ice cube molds. No, you need ice cube molds to make cubes for sure, but that's not going to help you out if you don't understand the process. Cloudy ice has impurities. That is true. That is absolutely true. But what are those impurities? We'll get to that. This one's fascinating. It's not wrong. In fact, there's a commonly used process to make large cubes or blocks for sculptures. You need to vibrate the water while it's freezing. First off, really difficult to apply. Not wrong. Layer and refreeze. This could be from some observation of someone looking at icicles. If you look at icicles, icicles are perfectly clear as well. And of course, there are people that just don't even know what you're talking about because they've never even thought about it before. And these people are sort of tough to deal with in these situations when you're talking about artisanal ice, such as the clear ice cube. So this picture here is a picture taken from the Detroit Free Press. It's something it's common to me. The first freeze is the best. You go out there in the lake, it's perfectly clear ice. You can actually see the ripples kind of forming underneath. And I think this picture actually kind of crosses out a lot of these things. You need to use boiled water. Well, no, you don't, because lakes freeze clear. Doubly boiled water, we already ruled that out. Distilled water, no, because lakes freeze clear. There's going to be a high concentration of total dissolved solids in lake ice. So these are not the right answer. And I think what this is getting us to is that what we need to do is we need to understand the process. How does ice freeze? And that's where you're going to get the answer to making clear ice. Okay, let's dive a little bit into the thermodynamics of ice, just so we kind of know where we are in pressure, temperature, space. Here's a pressure in the y-axis, temperature on the x-axis in Celsius. If you have a glass of water, then you're somewhere in the stability field for water in the liquid phase. And if you open up your freezer and you've got ice cubes, well, then you're somewhere in the stability field down here. If you've been going outside at night to watch the Neowise comet, well, then what you're watching is the sublimation of comet ice going from a solid directly into a gas phase. That's what that tail is that you're seeing. Okay, so for us, what we're dealing with is that we're taking water out of the tap, somewhere in this 25 to 30 degrees Celsius, depending how warm it is in your house, and we're trying to freeze it so we can cross this line from the liquid phase into the solid phase. We're not done with chemistry. Like all complicated problems, chemistry is typically the answer. So let's talk about dissolved gas solubility, because this is the answer. This is the problem with cloudy ice. If you're drinking a soda and you open it up, you notice it fizzes. Well, what that is that's carbon dioxide that's exsolving out of the liquid phase into the gas phase. And so all water has dissolved gas. Doesn't matter where you get it, doesn't matter where you buy it. If you open it up and it's in contact with the atmosphere, then there's going to be dissolved gas, predominantly oxygen and nitrogen. So let's talk about some of these other things that people are talking about. Well, you need to boil water. Okay, they're not wrong. As you increase temperature in water, you're decreasing the solubility. So high temperature water is going to have less dissolved oxygen than low temperature water. But then when you freeze the boiling water, you got to go back to the low temperature. And while you're doing that, unless you live in a vacuum, then your ice is in equilibrium with the atmosphere. And so water or air is going to quickly dissolve back into the water. So that it doesn't matter if you do it singly or doubly. It's the dissolved oxygen or dissolved nitrogen oxygen is going to go back into the water. Let's tackle the impurities. What I did here is I downloaded some data from Austin Water just to kind of get an idea of the total solids in Austin Water. I don't know the units of these. It's about 253. Here's the alkalinity. And then here's the dissolved solids and just the chemistry that's recorded from different bottled water. And you notice that, you know, in the case of dissolved solids, there still is dissolved solids in any of the bottled water that you're going to buy. It's not the picture of the lake ice tells you the dissolved dissolved solids and impurities is not the problem anyway, but it's sort of good to look at and sort of put the nail in the coffin in terms of does the chemistry of the water, you know, the dissolved chemistry of the water have an effect? And I would say from here, no, there's no evidence that's the case. Okay, let's get back to the problem at hand. Why is ice clear, and how do we get back to those magical days back in the 1800s when there was no cloudy ice? No one would just, you couldn't sell that if you tried, no way. And you wouldn't want to put it in your glass if you could. There's no reason to do it. That was something that was brought to us by the ice industry back in the 50s. So I would look at pictures of ice, current ice, and here's the god-awful crescent ice. And it shows you exactly what's going on. Perfectly clear ice. Look at that good ice on the outside of it. And then that inside just cloudy happening there. Looks like these people here, you know, they made molds. So they tried the ice molds, but still perfectly clear on the outside, horribly cloudy on the inside. Same thing here. Cloudy on the inside with some sort of interesting bubble patterns forming out here. And we'll show this in some other photographs. So the clue to the problem is the distribution of the clouds. The clouds, go open your freezer when this talk is done and look at your crescent-shaped ice, and you'll see the clouds are always on the inside. Okay, let's go back. The lake freeze approach. You know, I mentioned that when lakes freeze, it's a top-down approach. It's a lake freeze from the top, but there's always water circulating on the bottom. And when lakes freeze, they're always clear. So the answer to the problem is that when ice forms, it excludes dissolved gas. So it just makes pure H2O ice. There is no gas bubbles in the crystal structure of ice. There just can't be. When ice freezes up here, any of that dissolved gas is able to go into the water that it's in equilibrium with. And so the water is always going to be the sort of escape mechanism for any of the dissolved gas that's out here. And you can form bubbles. And if you go out in lakes kind of later in the year, you will get a bunch of bubbles that are formed. They happen for a variety of reasons. And you'll see in ice cubes that I make, you still do get some bubbles. But the key thing you have to do is you've got to simulate the lake freeze approach. You got to be able to make ice cubes, but always have water on the bottom. And so, you know, you can imagine my house, you might be getting the flavor of some of the hobbies I get into. You know, it's sort of, my wife puts up with me quite well. You know, it's almost like an episode of Curb Your Enthusiasm sometimes. You know, I come up with these ideas. It's like, I need to simulate a freezing lake in my freezer. And, you know, the family sort of nods and waves, like, if you need to, go do it. But if you're going to make clear ice cubes, you need to do it. And so that's what I did. So how did I do that? Well, I bought a giant tub shown here. It's a big plastic tub, and I had to put some supports down in the bottom of it. And these are just PVC tubes. And then I insulated the tub with insulation around the sides of it and around the bottom of it. And so that essentially is my lake. The second thing I had to do was build or modify the ice molds. So I bought just standard silicone ice cube molds. But what I had to do is drill a hole into the bottom of each one of them. And what that's doing is it's allowing, when the ice forms, it allows that dissolved gas that's going to become supersaturated to diffuse into the reservoir of water that's always going to be at the bottom of it. And that's how I'm going to get the clear ice. Now, obviously, if I left this thing in the freezer long enough, the whole thing is going to freeze solid, and that's fine. And you'll see from the photographs that I did that in the last batch that I made. But all that cloudy ice is going to be concentrated in the very bottom of the tub and not in the molds on the top. Okay, so sort of a step-by-step process. You know, like I said, I made these little PVC tubes here. All that does is suspend the ice molds at the top. And then you can see, you know, just fill it correctly, get it to about the right level, and then put it all, oh, and that's the other thing. You got to buy if you want to do it in a mass quantity, I make 32 at a shot. And that's, you know, for just kind of giving to my friends, that's a good number to make. Then you got to buy a dedicated chest freezer to do this. So I take this whole tub and I put it in the ice freezer, shut it, and then come back from time to time. It takes about 27 hours to do it right. It's really hot in Austin, Texas right now. It's hitting hundreds. So it does take a little longer. And I'll just point out, there is nothing environmentally friendly about ice cubes. Doesn't matter if it's the ones I'm making or the ones that are being made in your freezer. It is a energy intensive process. So here's the picture of the ice forming at 6 p.m. And I just did sort of a poor man's time lapse. Here's 3 p.m. next day. And you can see you're building up a nice layer up on the top, just like a lake would in mid-December. What's interesting, and I don't have an explanation for it, is it's sort of a mottled surface on the top. It's not perfectly flat, and I don't know exactly why. But you can see the important thing here is that the ice is perfectly clear. And you can also see the little holes kind of down here at the bottom of each mold. So that's 3 p.m. Tuesday. Here we are, noon the next day. The freeze layer is getting thicker. We're getting some ice is forming. This is actually rime. Rime is sort of a sublimation process. There's a lot of humidity in the freezer, and that humidity is freezing onto that solid surface. And so it's going right from vapor to the solid phase. So that's what rime is. And you can see the ice cubes are starting to form, getting a little thicker. You might see some interferences down below there. And I'm going to highlight these two ice cubes right here. They're still perfectly clear, but you'll see what happens. Oh, I was wrong. Which one? It was these two ice cubes right here. Okay. All of a sudden, they're getting a little bit cloudy, and they're starting to protrude from the ice mold a little bit. And it happens every single time I freeze it. There's always one or two, we call them fugitives, that sort of pop out, and they start to get pretty cloudy. And you can see, you know, as we get to 11 a.m. Thursday, then they're really starting to pop out, and they're perfectly cloudy. My hypothesis on this is I don't know the answer, but I've got two ideas what's going on here. One of them is that, you know, ice as it expands or as it freezes, it expands. And so there's a volume issue that's happening here. But also as the ice freezes, like I said earlier on, dissolved gas does not go into the ice structure. And so you're building up a lot of bubbles of ice that are forming down in the bottom reservoir of the water. And you need to, that pressure has to go somewhere. And so I think that pressure, all of that gas is making its way up into these two ice cubes. And so here they are at the end of the freeze. And you can see these little guys popped out entirely. But everything else, you know, it's that perfectly clear ice. Look at that all the way through. Really nice. Except for these two right here. So the hypotheses, I think this is the right one here. Gas bubbles, you know, exsolve or dissolved gas exsolves into gas bubbles that creates pressure in the bottom of the reservoir, and that pressure's got to go somewhere. And so it just finds the weak link and pops those ice cubes out. And so what's interesting, and from another standpoint, I don't know if I have no, I didn't bring another slide here. Let me just pop back a little bit and bring up some chemistry. Remember this slide here. As you go down in temperature, you actually increase the solubility of a dissolved gas. So why, when we freeze, does do these bubbles form? And I think the reason is because even though the solubility of cold water, or the solubility of dissolved gas in cold water is higher, the fact that we're excluding the dissolved gas from the ice creates a supersaturation issue. And that's why these larger bubbles are actually forming inside of it. Okay, so now I'm just taking some pictures of what we got. So this is turned on end. I took the ice cube, the tray out of the water, and those are those two ice cubes that popped out. And so we're looking sort of at a profile of my lake, the lake freeze approach. And you can see perfectly clear ice up on the top, just like you want. And then down here, you know, everything's going to chaos. That's where that dissolved gas eventually had to come out of solution and form ice bubbles. But for my process and for what I do, the important thing is that all happens below the surface of my ice cubes. And so if you're going to duplicate this at home, and I hope somebody's going to, then just make sure that you keep that ice tray, you know, your molds higher than that layer down there. Here's what they look like, taking them out. And just like I said, you can see all that cloudy ice is built up just in those two that popped out. But look at that there. You got beautiful ice cubes to do anything with. You can even just put them in water. There's some pretty interesting ice patterns that form. This is a close-up of you know, some of these patterns that will build up in the bottom. And I don't know exactly how to explain these. Kind of my latest, I'd love to do time lapse. I think it'd be cool to put a camera in the freezer and watch this, but I've not done that yet. I might try to convince my kids to give it a shot and see if we can do something. I think, you know, one of the things that might be going on is that a bubble, you know, ice freezes, it's a top-down approach. Ice freezes from the top, makes its way down. So my guess is that a bubble may form, and then as the ice builds around it, it's just slowly pushing ice, or the bubble down to the bottom. That's one idea. Because certainly once the ice is formed, there's no way that a bubble is moving up through it. I don't know, just a curious observation. Again, the whole point here was clarity. You know, if you're going to be judgy about these things, clarity matters. You know, I said it in the beginning, if we're talking cocktails, appearance is one of the important aspects of a cocktail. And ice is an important ingredient. And from this coin sitting down in the bottom of the ice, you can see that we've got very high clarity ice. Not perfect. We do have, you know, some of these little bubbles that are forming here and there. I don't care about those. In fact, I think they're kind of interesting to sort of look at them as the ice is melting. You know, obviously, if you're building an industry around this and selling this stuff, that would matter. For me, that's not a concern whatsoever. And I just asked the question to all, like, why settle for cloudy ice when you can have clear ice? I mean, let's be honest. What would you rather drink a nice cold glass of water out of? Something like this here with this ice cube that you can barely see, or this just atrocious crescent-shaped cloudy ice? Ugh, I don't even want to think about that. I go for this. So this is what I'm left with. And the process, you know, overall, I can make 32 ice cubes in about, it's like 27, 28 hours. That's certainly enough for my family and I for a couple weeks. But they're a pleasure to use and to enjoy. So just to get back, you know, answer some of the questions and what you can take home from this. You know, obviously, if you want to make clear ice cubes, I highly recommend it. It's actually really fun. I don't know how to scale it down to something smaller than what I've got. There are some ideas, but my system works for my needs. But if you're not going to make clear ice, at least when you hear someone talk really loudly about how you make clear ice, and you hear them say some ideas like using doubly boiled water, well, you can confidently jump into that conversation and say, no, that's not true at all. And if you don't want to get into the details of it, just ask them, if that's true, then why does lake ice freeze perfectly clear? And the answer is because it's the process. It's how ice forms. And the lake freeze approach is one of those important processes. I'll conclude on this slide, and I'll just use this, and you know, I'm pointing to a few of you in the crowd. Next time that you open up one of your more expensive bottles of scotch or whiskey, give me a shout, give me a call, and because I'd honestly hate to see you enjoy it with a cloudy ice cube. There's no reason for that anymore. There's no excuse. for cloudy ice. Clear ice can happen. So with that, I'm at the end of my talk, and my little sunset slide is taken from Lake Michigan, overlooking the west, obviously, it's sunset, but you can see just how much clear ice actually forms at various times. And I'll ask questions. I'm gonna open up the chat thread. If you guys wanna ask a question, I'm not sure what the process is of that, but Aaron, how do you, or Evan, how do you wanna handle questions?
So you have a few in the chat right now, and
Okay.
we can also open up the microphones, but perhaps let's answer the ones in the chat. If you want to maybe read those out before you answer them.
Okay, sure. Let's see, the first question, we'll start from the top. If I put my awful cloudy ice cubes in a glass of water, I can enjoy cold water right away. But if I leave that glass out, I eventually get a precipitate in the bottom of the glass once the ice is melted. What is that? It might be calcium carbonate. Boy, yeah, if you got precipitate coming out of your ice, phew, I don't know what to say there. You know, there are sort of weird things that can form. I don't know. Those are solids. I mean, if it's a precipitate, there could be dissolved carbonate that's going to precipitate out. You got to get a lot. You know, the volume of ice in a glass, it's a pretty small ratio. So I'd be surprised that you'd have so much hard water that you could supersaturate your glass with a carbonate. So I don't think it's a carbonate precipitate. Maybe, I don't know for sure. Michael Young, I go to the next question. You asked the right question. I'm gonna give a shout out to Georgia Sanders and Kristen Tuchek. Early on in this process, I was working in dissolved gases. I was working in the Department of Geological Sciences, and I ran a few experiments of putting water in a headspace vial and pulling a vacuum on it, because I thought the approach here was just what Michael suggested, which is if you create a vacuum that will remove the exhaled oxygen from it. Yes, in theory that works correctly. In practice, it just doesn't work. And so I took a bunch of headspace vials and I pulled pretty high vac, not turbo, but higher than anything you'd have at home. Certainly higher than you'd get from, say, one of those wine preserver kind of like, pump things. So it doesn't work in practice. So no, it doesn't work, but I did try that because I thought that would be a very good approach to it. Is the gray container food safe? Sure. I highly recommend everyone uses food safe containers. For another one from Michael Young, have you measured the survival time for cloudy versus clear ice? Well, here, this glass here is, I'm down. Oh, I guess it doesn't really come up in the background. Let me, well, I'll save time on that. Yeah, of course. Clear ice lasts longer than cloudy ice. Cloudy ice has a much higher surface to volume ratio, and that's the key issue with the melt rate. I don't know if there's. Here we go. Another one. I'm thinking Everclear grain alcohol versus Scotch. If you're drinking Everclear, you're gonna go back to college and you're gonna do great. That's a great place to drink that. Let's see. The freeze rate must matter. If too fast, this is one from Claudia Mora. If too fast, the gas bubbles may be trapped with crystal growth. How can you change the freeze rate? Freeze rate, you know what, Claudia, I'm going to answer that on two sides. The freeze rate, and also something that I've noticed is not only the mechanical properties of ice. I noticed that if I let the whole container freeze all the way through, then it actually becomes much more brittle, and I get some fractures that'll form in the ice cubes as I pour water or liquor onto it. And so what I'm thinking is that, with thermodynamics, when you've got, as long as you got water in the reservoir, that ice is pinned at 32 degrees. And so it could be that once I let the container freeze all the way through, it can drop to the temperature of the freezer, which I'm not sure what it is, but it might actually become too brittle. So the freeze rate that you're asking does matter. I think it matters. We sort of need to, just like glass, anyone who's done glass blowing, you need to anneal the glass. But certainly with the freeze rate, as you cool it, has to have an effect. But I haven't experimented too much with that. That gets me to the end of there. Any other questions out there? Any other ice enthusiasts in the crowd?
So Toti, I guess I'll ask, is there still some sort of industry for ice cubes in the world today? There are businesses out there that provide cocktail ice cubes?
Oh, there definitely is. And you can imagine that as I was doing this, I kind of had my, my eyes on the prize, and I thought like I could certainly profit from this somehow. And, I kind of did the math on it. So, and where this, there's a bar owner, or a bar out on E6, makes amazing old fashions. And he ended up living across the street from me. And so we talked a little bit, and he noticed, as all good purveyors of cocktails noticed, he saw my glass. He's like, whoa, that is a really nice ice cube. And so I showed him the process, and, he told me that he goes through 32,000 ice cubes a year, clear ice cubes a year, in their old fashions. And they purchase them for something on the order of 75 cents to 90 cents a piece. So that's just one bar. And so obviously there's an economics there, but I looked into it a little bit. The available freezer space in Austin is limited, and transportation costs are huge. And it's a tough industry to scale up. There is a more efficient approach to scale this up. Let me see if I can. Let me share my screen one more time and show you one last photo here. And it's not a question, but I'll point it out. It's the Klein process, the bottoms up approach. They've been making ice sculptures for years. Artisanal ice has been around for a long time. That approach, it uses the bottoms up approach. And so what they do actually is they freeze from the bottom. They continually circulate the water and vibrate it, like the one suggesting that you need to vibrate it. And so the ice freezes from the bottom and excludes any dissolved gas, and they make perfectly clear ice cubes. And so there's some big ice, I forget what they're called. There's a couple big ice companies in town that are have an industry around it. What they're doing is and the guy was investing in the Klein process that has this bar downtown. They freeze giant blocks of ice, and then they use a bandsaw to make them. So yeah, there's an industry around it for sure.
Toti, this is so I'll just ask this. If you were to make an egg-shaped ice cube, now I realize that you can't really do that, but I'm trying to think of by creating something that has minimum surface area, because a sphere has a smaller surface area than a cube.
That's right.
Could you make the ice cube last longer, and it would give you a little bit of an edge up, so you'd have an ice egg instead of an ice cube? Yeah,
the sphere is the ice sphere is the perfect way to cool your cocktail, because it's got the lowest or the highest volume to surface area, and so the sphere will always melt much more slowly than the cube. I've tried it, I've failed. I did buy a couple some molds, and I tried to position them correctly, and it just became a problem altogether. So I backed off of that. I didn't put any pictures in here, but I can share them with anyone who's interested. I've actually gone through here, and I put lemon slices in each of the cubes for summer, when you're looking for like a good gin drink and you want to kind of hit it up with a little extra lemon flavor. The sphere though, Michael, I think with competition, you got the guys who are using the people, the industry that's using the Klein process. They're going to be able to make 700 to 800 ice cubes per block. And so it's going to be tough to compete with them, but they're never going to be able to do two things: make a sphere or put something inside of that ice cube. And so that might be the sort of competitive advantage on it. Now, I did see one company, what they're doing is you buy the clear ice cubes from them, and then they've got this sort of press. It's an aluminum press, and it's shaped like a sphere. And so you take a cube and you make it into a sphere.
Oh, that's lame. That's just cheating.
It's totally cheating. Yeah, I agree. I'm with you there.
I would never put a pressed ice egg in my drink ever.
I'm with you. I would never do that. I would certainly never put a crescent-shaped cloudy ice cube in my drink.
So you have a few more questions in the chat. How did they transport the ice in the 1800s without melting it?
Yeah, great question. What a fascinating industry. You got to imagine, the first step is to come up with the idea. And then the second step is to identify the source. And then the third step is to transport it. And so 1820s, you know, you're talking ships, rail cars, not even across the, you know, horse. What I read about insulation is that they started with sawdust. That was the primary tool they had at their disposal. A lot of sawdust in the mills, you know, up in New England, in the wood mills up there. But before the sawdust, they actually started with hay. So they would pack, you know, these ships as tightly as they could. So again, the cube shape matters because you're gonna get the biggest bang for your buck in terms of filling up, you know, a ice house with ice cubes if they're cubed. But then they would pack it with hay and they'd pack it with sawdust and then store it. And you know that to go from Boston to Calcutta on a ship, that's 4 months. And so you got to have some pretty good insulation. So I don't know everything about how they insulated it, but I imagine they buried it quite a bit. Yeah, it's hard. Transportation is key. Refrigeration was big, and that's, you know, that feeds the follow-up question is what killed the ice industry? And you know, at the end of the day, what killed the natural ice industry? And what killed the natural ice industry is the artificial ice industry, and that was fed by electricity, and it just became cheaper to build it, you know, or make ice locally and cut the transportation costs. There's a question about why you use pipes at the bottom of the tub and why you insulate that. Well, Mehdi, that was my way of building a lake in my in my freezer. I know it's as funny as that sounds, but I needed to essentially build a lake. And so the way I made a lake, you know, what is a lake? And a lake is insulated by, it's a body of water that's insulated by the earth and has its cold surfaces on the top. And so I use that to simulate the lake freeze approach. Claudia, yeah, if we froze Elephant Butte. Hey, Claudia, you want to chime in and point out some of your early observations on ice freezing in Lake Michigan? You can unmute if you want to. Yeah, eventually, if you if you freeze a dirty lake, you're going to get dirty ice there. Enough said. Do I recommend clear ice for pina coladas? I recommend. That's my brother. Yes, I absolutely. I recommend clear ice for everything. You know, certainly Coca-Cola, ice cubes in water everywhere. Everything's better with clear ice. Any other questions out there?
More of a comment. I'm a graduate student at UTIG, and I'm actually researching like salty ice for the Europa Clipper mission. And kind of related to the question that Claudia asked about freezing rate, that's something I've been like incredibly obsessed with in terms of like how impurities partition into the ice when you have like faster freezing rates. So one of the things with lake ice is that it is fairly impure, right? So even if you have a high freezing rate, that kind of promotes like a more of a planar interface. Is that right?
I guess, I don't know. I'd love to. Are you taking videos of ice cubes forming?
Oh, no, it's very much like looking at it in terms of theory to predict what our radar is going to see on the Europa Clipper mission. So okay. Yeah, more of the theory side.
Yeah. Well, like all good theory, we need experiments. I would, it's, you know, every time I take those ice cubes out of the freezer, you know, I'm just more and more fascinated by the freeze approach. And, you know, I think some of the bubbles that I see, once you get the cloudiness away from the ice, the bubbles that are left are really cool. They're just fascinating patterns. And I don't understand that. And I certainly don't understand I have no idea what the bottom of the ice surface looks like. You know, I have a freezer that there's no way the temperature gradient is constant across it. It's got to be pretty heterogeneous across it, and that's certainly got to affect the freeze surface. But yeah, I'd like to, I think we should take some videos.
Yeah, I'd actually love it if you could if you had some time and you were bored, if you wanted to play with like salty ice in your freezer. I'd love to see what that did.
Maybe, yeah, we could get people away from putting salt on the rim of their margaritas and just salty ice. Yeah. Kind of has a good name to it, right? A feel to it, yeah.
Well, Toti, that was a great talk. Very interesting. If there are any more questions, now's the time to ask them. If not, thank you very much for the talk. It was a great talk.
Hey, thanks. It was a pleasure. Yeah, it's a good time.
Thank you very much.
Hey, and I hope you can enjoy a nice cocktail this evening. Cheers.
Cheers. Oh, you got one more question. Any inert chemical that you can add to lower solubility?
Yeah, helium. I think I'd have to look back at the solubility chart. Oxygen, CO2 is the worst, right? CO2's got the highest solubility. So that'd be the worst thing to do. Oxygen has a high solubility. Methane, is a pretty high solubility. I think nitrogen is the next, but then you got to make your way up into the noble gases. And, it's a longer story for certainly. It's a story for a cocktail. How about that? But we, one of the things we did try early on was just bubbling, nitrogen through the bottle, the water before we froze it. In fact, that's a common technique. When you're doing lab experiments or if you're doing lab chemistry, you often want to get the dissolved oxygen out of the water. And so the process there is to bubble the water with nitrogen, and that kicks out any of the dissolved oxygen and replaces it with dissolved nitrogen. So you're left with dissolved nitrogen, and eventually, if you're to freeze that, if you're able to maintain that, in a container and with a headspace of nitrogen and freeze it, you would still have dissolved gas. But I think hydrogen and helium have the lowest solubility. How do you get the molds out of the frozen lake? I've got children, and that's their task. We let it, we take it out, and like I said, for some of the mechanical properties, we'll let it thaw for just a little bit. And then we pretty much just like drop it, kind of smack it on the ground, and then just break them out. And so the timing is key. Under normal conditions, it's about 28 hours for a freeze. And so if you take the molds out when there's still water in the tub, it's really easy to break it out. And if it's frozen all the way through, then it's a little bit harder. But I just sort of break them, just kind of drop them, hit them on the ground.
Well, all right, great talk, Toti. I loved it.
All right, guys. Hey, that was really fun. I appreciate the opportunity.
Thank you very much.
Yeah, anytime.
Everybody have a good weekend.
You too.